So let's start then, okay? Okay.
Yeah.
So welcome everyone to this Friday IISERM-Mohali colloquium. It's a pleasure to welcome Professor Stephan Tillmann from the University of Sydney. So Stephan is a professor at the University of Sydney, and he is also the executive director of Sydney Mathematical Research Institute. And he is also the deputy director of the Australian Mathematical Science Institute. So Stephan is Stephan is an editor of the Journal of Combinatorial Geometry, and he is a very active and prolific mathematician from Australia. So it's indeed a great pleasure to invite you, Stephan, to IISER-Mohali. Though virtually, but I hope you will have the opportunity to visit us in person at some point of time. Yeah, so you can share your screen. So today, Stephan will be giving the lecture on convex projective structures that you might have already seen. So Stephan, you have to share your screen.
Yeah, thank you very much for the introduction, Krishnendo, and thank you very much for the invitation to speak. Indeed, I've never been to India, so I was meant to go in 2020, but then things got in the way that we all know about.
Yeah, absolutely.
That's the reason why I'm speaking to you from the traditional land of the Gadigal people of the Eora Nation, on which the University of Sydney is based. Yeah. And it's a pleasure to give you this lecture here on moduli spaces of projective structures and manifolds. Okay, so I'm very happy to be interrupted with questions at any time. You can either use the chat. I'll try to monitor the chat, but maybe if I don't see it, Krishnendo, please alert me to it. Or you can also just unmute yourselves and speak. Okay, so I want to talk about these moduli spaces and some of the things that I liked about them. But before I do this, I guess I should introduce real projective geometry. Yeah, so I mean the projective space, most people are familiar with, but let me take a thinner pen. So the n sphere 2-to-1 covers just by the interpedal map the real projective space Rpn, but I also think of this as a space of lines in Rn plus 1, right? And so what we get from this is then we sort of get, of course, the group action from the general linear groups. So sorry, my palm got in the way. So GL n plus 1 R, of course, acts on the lines. And in Rn plus 1, yeah. And so this gives us an action, of course, of GL n plus 1 R on Rpn. But of course, scaling doesn't make any difference. So we can actually go to PGL n plus 1 R, yeah, because scaling preserves the lines. Okay. And so this gives us sort of a framework to do geometry in the sense of Klein. So Klein really just says, in this sense, I get a geometry as some structure where, as a group, I take PGL n plus 1 R, and as the space, the underlying space, I take Rpn. And then anything that's kind of invariant under this group action is a geometric property. Yeah, so this is how we can try to study things. And this might at first maybe seem far too flexible to do anything useful. So what I like to do is I like to sort of restrict to some other special sets inside here. So what I want to do is I sort of want to think inside here of, well, I mean, one thing is I can sort of look at the complement of a hyperplane. So this is just basically like a copy of Rn, yeah? And inside this, I will look at certain sets that I usually denote omega. And I will think of omega as either maybe, I mean, one notion is I like to think about convex sets. So these are just sets where the intersection with the line is connected. Yeah. Then I like to think about properly convex sets. So they have the property that the if I take the closure, then this is still contained in this copy of Rn. Yeah. And then the last thing, becoming even more restricted, is strictly convex. And so this is basically properly convex plus no line segments in the boundary of this domain that I have here. Okay, so maybe a little quiz. So if I show you this this set here, is it convex? The
yes,
quiz is very
it's
easy.
convex.
Yeah.
Yeah.
Yes, it's convex. Is it strictly convex?
It's strictly convex, yeah.
So strictly convex was meant to be no line segments in the boundary of the set.
Oh, I see. So it's not strictly convex, that's what you're saying.
Yeah, it's not strictly convex, exactly. So here I see some, I see some straight line segments in the boundary, so it's not strictly convex. Okay, so what about this set here? So this here is just properly convex. This set here?
Anyone from the audience? This is also not strictly convex, right? You have a line there in the top.
I have a line here, yeah. So this is also just properly convex, yeah. So when I draw something like this here, something like this here, that's okay. That's strictly convex, yeah.
Yeah.
And then maybe if I sort of think about Pac-Man, is Pac-Man any of these?
No, this is not convex, right?
No, this is not convex, exactly. So if I take this line here, then I see two pieces of intersection, and that's not connected, so it's not convex, yeah? So not convex. Mm-hmm. Okay, so these are the kind of objects maybe that one think about. But to make it more interesting, I'm going to say geometry, right? I mean, geometry, we usually think sort of lengths, angles, and things like this. So, but before I actually go into this, let's change. So often I change perspective, actually. I mean, here I'm in the real projective space. I mean, I've drawn sort of the two-dimensional picture where I have the projective plane here. And of course, it's covered by the sphere. And so I have some domain in here. And if it's strictly convex, then I mean, it's contained in the complement of some line. So let me just indicate a line here. Yeah, so this is indicating a line. A line goes up to basically a great circle. Yeah, so a line in the projective plane goes to a great circle on the equator on the sphere. So this domain will have two lifts, one sort of on each hemisphere. And often what I will do is actually I will identify this domain that I have here with one of these two lifts. And that has a nice thing that when I sort of act, I mean, here in this picture, I act by PGL n plus 1R. But then on this picture here, I basically get an equivalent action, but I can actually restrict to matrices that have determinant plus or minus 1. And this gives me access to things like eigenvalues or traces. And other sort of useful properties of matrices that they don't have here. And they will actually sort of, they play a good role in this game. Okay, so then geometry, I said I want to have some geometric properties that I can work with. And there's a wonderful thing called the Hilbert matrix. So the Hilbert matrix works as follows. So if you have some kind of domain, here's my domain omega, and I have 2 points in it, say A and B. Yeah, I want to define a distance with respect to omega between A and B. And the way I do this is as follows. So you take basically a straight line connecting them. And because I assume that omega is convex, it doesn't need to be strictly convex. So let me so make it properly convex by putting something straight here. So it meets sort of, I get sort of points, unique points of intersection here, X and Y with the boundary, yeah? And it's some patch that's Rn, and I just choose any norm, basically, any Euclidean norm on it. And then I define the distance as follows. So I say it's a logarithm of, so I take the norm between, so the distance, yeah, Euclidean distance that I've chosen on this patch between x and b, and I multiply it times the distance between y and a. So these are the two long distances I see here, this one, and then just divide by the two short distances that I see here. So x minus a and y minus b. Okay. So this is kind of good, right? This number here that I get is going to be bigger or equal to 1, yeah? Or actually, if these are distinct points, it's strictly bigger than 1. And so when I take the logarithm, I get something that's strictly bigger than 0, yeah? So it's some kind of non-negative number. And now I actually claim that it's symmetric. And so it's easy to see that it's symmetric. Yeah. It's, of course, we've got positivity. And the triangle inequality is maybe a little bit tricky, but I'll leave it as an exercise. It's sort of a fun thing to try to check, actually, that satisfies the triangle inequality. Okay. And another thing, it's invariant, because that's also not so hard to see by this definition, invariant under the action of PGL n plus 1R. Okay, so I get this kind of notion of distance that I can use, yeah? And so what does this now give me? So yeah, so invariant under the action, I mean that, yeah, D, so I apply some matrix M to omega, and then I have M applied to A and M applied to B, then this is the same as D applied to omega between A and B, yeah? And so in particular, if M applied to omega is omega, so if your matrix actually preserves omega, so then it follows that it is an isometry of this domain, which is just wonderful, right? And so in general, basically, so you can actually show that if your domain is strictly convex, so if omega is strictly convex, then actually, so a matrix that satisfies this here, so I call the set of all such matrices PGL omega, just in a simplified notation. And so if omega is strictly convex, then in fact the isometry group of omega is just PGL omega. So you get this really nice equality here. And if it's properly convex, then it's of finite index. So if you have properly convex, then this inclusion is of finite index. So that's still good enough for what one might want to study. Okay. Is there anything else I want to say? So maybe one other thing that I want to point out here is that from this kind of definition, it's not too hard to see that this thing here is what's called a Finsler metric. So this here is a Finsler metric. So maybe people who sort of like is there anyone here who likes Finsler metrics? You can just raise a hand if you do. No, okay. So I will not write down the Finsler line element then. Yeah.
But I know a few people who likes it in India, the Finsler kind of metric. Yeah.
Yeah. Okay. So let's do it. So yeah. So for the Finsler metric, I sort of pick a vector u in n sort of based at a, and so I want to write down the line element. Yeah. So this looks like, so if I look at f omega of the point a in the vector u, yeah. So then in this setup that I have here, so just going to be the norm of u times, and so now my space management on this slide is terrible. I always have the issue with this iPad that it's not the same as having 6 blackboards, but maybe my space management on blackboards is also not so good. So we'll see. So let me move things around. So here's my line element, yeah, and it's 1 divided by norm of A minus, and so now it's basically a question of where I come from. So I come from X, so norm of A minus X, then plus 1 on A minus, and I have Y, yeah? So where I'm going to. So this is what the Finsler line element looks like. And of course, people who sort of like Finsler geometry can do nice things with this. And there are also some really nice results sort of proved in this context. But I don't think I will sort of go into them. Okay, so then here's some nice facts. One thing that's been known for quite some time is a fact established by Kay, that this thing here is actually a Riemannian metric. So this Finsler metric is Riemannian if and only if the closure of your domain is an ellipsoid. And then maybe it's not so surprising that then actually your geometry that you get, so this kind of Hilbert geometry here, is isometric with hyperbolic n space. Well, there's a small lie in here because actually you have to choose the right constants in the definition of the metric, but that's fine. So you get something that's hyperbolic space. And another sort of fun fact is that this here also becomes a non-vector space, or isomorphic to a non-vector space, if and only if your domain is an n simplex. So that's another interesting thing. So maybe to point out how this goes is, so let's just draw sort of the three-dimensional picture. So here you have sort of your n simplex. Maybe it's spanned by some vectors E1, E2, E3, yeah? And so then for any sort of point x inside there, you write x in projective coordinates as e to the a, e to the b, e to the c, yeah? And you map this to, so in, here I'm doing the two-dimensional picture. So in the plane, you map this basically to a linear combination of the form AV1 plus BV2 plus CV3, where these vectors are chosen so that the sum is 0, yeah? And so what you get is kind of, I mean, you have these three vectors, say V1, V2, V3, they sum to 0, yeah? And this is the norm ball, so unit ball here looks like this here. It's just a regular hexagon, or a hexagon sort of spanned by these three vectors. So this is your basically norm ball. And so one thing you see here is, so this is a ball of radius 1 in this norm vector space, yeah? And so what you see is that if you take the circumference of this ball and you divide by the diameter, so that is what? So what's the circumference? The circumference is actually 1, 2, 3, 4, 5, 6. So circumference is 6. And the diameter is 2 because the ball of radius 1. Yeah, so the diameter is 2. And so that's 3. So this is kind of a geometry in which the number pi, because that's how we define pi, right? Pi is the circumference divided by the diameter. And that in this case turns out to be 3. Yeah. So it's kind of what the Bible tells us pi is. Yeah. So maybe it's about this kind of metric. Okay. So maybe moving along. So what kind of structures have, or what kind of manifolds have structures modeled on this? Because I've just defined sort of geometry in a very sort of general sense. And the question is what does it apply to? And so of course, if you think about what I have is, well, as my domain omega, I could of course take an affine patch, yeah? So an affine patch Rn, and I could sort of take, I mean, I don't even need to take all of these. I could also just take some kind of subgroup inside here. I could focus on some G comma omega inside it, yeah? And so one thing I could do, for instance, is I could just take, say, so if you take, say, the orthogonal group, yeah, semi-direct product with Rn, then what you get is really Euclidean geometry. Yeah, so that's one thing I see here. Or if you take something like PO 1n, that's also a nice subgroup again, yeah, of GL n plus 1r, and I take sort of a unit ball, dn, yeah, then this gives me exactly this, what I said before, this kind of, I think of this is a hyperboloid, this is everything preserving it. And so this is hyperbolic geometry. And so similar, I sort of get elliptic geometry by taking PON, yeah, and all of RPN, yeah, and this is elliptic. Okay, so I see basically everything that I need as geometries inside inside my space. Oh, PON plus 1. Okay. So these are kind of the main constant curvature geometries that we have, yeah. But what this framework allows us is slightly more flexible, because now we can sort of move between them, yeah. And there's sort of lots of geometries also in between. And so what kind of things does one get? So let me maybe go to an example just to do one. So here's one puncture torus. And so one puncture torus is here. So I've chosen a fundamental domain. And then these elements of the fundamental group sort of represent these kind of two loops here. And so I'm thinking about representations. I said before, I often like to work with the spatial linear groups. So here I'm just saying SO3R. And so I want to sort of think of, well, I associate sort of one matrix or one element with alpha and one element with beta. And then I could really just see what I get, right? And so just to draw sort of a picture, I mean, if I think about this is my surface S. If I think about the universe as a cover, the easiest way I find is to just think about it as a hyperbolic manifold. So here's my maybe universe as a cover. So I've chosen a fundamental domain here. So I make this green. And so under the action, of course, I get this kind of tiling of the fundamental of the hyperbolic plane. I could just keep going forever. And on this, I have an action of the fundamental group of S, yeah? And now I want to, so this holonomy representation that I have here, I used to basically define a developing map into, yeah, maybe an affine patch. So here I draw myself sort of an affine. This is supposed to be represent some R2 inside RP2, yeah? And maybe, yeah, and these vertices will go somewhere under, I mean, I really just pick one point, right? Once I pick a point, then basically the action tells me where I have to go, because I'm sort of acting here by maybe beta and by alpha. And so then once I sort of pick one point, this basically determines sort of where everything else goes. Yeah, and so maybe I'm lucky and I get some kind of nice uncollapsed domain here. And then of course here I act by these kind of holonomies that I have. Yeah. And so with this, I can then sort of propagate the tiling, whatever it does, right? So let's maybe look at some examples, just to see some, I mean, see this in real life. And so here's some examples. So here is sort of one example where maybe, yeah, I mean, maybe here was your fundamental domain and you had some matrices, or maybe not you and maybe not me, because this is from Thurston's notes. So maybe Thurston had some matrices and started generating this picture. And so where is this, what is the image of the holonomy? In which group does it land? Well, I guess your guess is as good as my guess. And when you look at this picture, what kind of structure do you think you're looking at? And certainly not Euclidean, right? Because we seem to be changing changing things. Yeah. Or does someone want to answer? Well, I see someone has unmuted themselves.
This is hyperbolic, right?
So to be hyperbolic, I would really need to preserve sort of a circle of some sort.
Okay.
But here, right, and this here sort of seems to be, and the way, if one sort of looks at this picture and these kind of trajectories here, right, there seems to be sort of some fixed point somewhere here that sort of things sort of converge to, yeah?
Yeah.
Yeah. Yeah. So the so what we see here is actually, I mean, this is maybe not quite as familiar. It's an affine structure that we're seeing here. Yeah. So it's a representation into the affine group where it's almost like the Euclidean isometries, but you actually allow yourself sort of the general linear group rather than just the orthogonal group. Yeah. And then the hyperbolic example, I mean, that actually looks like this one here, right? This is a nice round circle. So here, for some reason, I've sort of chosen the fundamental domain. Maybe here's my fundamental domain. And the action, right? So when we sort of look at what happens here under this action, it seems to preserve, yeah, a nice circle. And so this is actually where this here comes from. So this here would be an SO 1, 2. And then this one here, right? And this is maybe sort of surprising. I mean, you sort of see these things, yeah? They're sort of crazy shaped objects. And you think that there shouldn't be any group that divides this, right? I mean, why should there be a group already preserving? I mean, if you draw any old sort of strictly convex curve, yeah, right, you would think it's only the identity that preserves this. Yeah, and it's very hard to guess that there's actually an interesting group that does it. And this way you sort of generate them. So I have no idea what this, yeah, whether it's sort of a good characterization of this one, but there's something that preserves this domain here. And this is a strictly convex example. So this here is strictly convex, this here is strictly convex, and this here is, this sort of has a problem because of this fixed point here. Okay, here's another construction. There's some lovely examples by Thurston and Sullivan that I just briefly sort of want to touch upon, just to so think about what happens in terms of actions. So what they do is they say, well, look at sort of this family here, where you take yourself matrices e to the minus 3t, e to the t, e to the 2t, yeah? Okay. So, and what this gives you is it really gives you sort of a flow, if you wish, on RP2, where you have one source, one sink, and one saddle. So the way to see it is, I mean, I sort of represent my, the three, I mean, this here really just as a matrix in R3, right? It has 3 eigenvectors. Yeah, I mean, everything else here is supposed to be 0. Just the standard unit vector. So they give me 3 points in the projective plane. And then what's preserved between them is, of course, the lines. Yeah, so here, so the lines containing them. Okay, like so. And maybe I think of this here as the class of E1. This here is the class, yeah, this is sort of E2. And this here comes from E3, yeah. And so then E1 is sort of the source, right? It's sort of the repelling fixed point. And then when I think about E3, that's a dominant one, right? That's the sink. So everything sort of flows in here. And then E2 is the saddle, yeah? So what you see here is that, I mean, here we're flowing in this direction, so here we must be flowing in this direction. Because I sort of think of this as a projective image, right? And this here comes back here. And so, so here I go out, and so similarly here, I go in this direction, and I come in here again, like so, yeah. And I could sort of draw more flow lines, right, in this kind of picture. And actually the dynamics of these transformations, I mean, here might seem very simple, but this is really what sort of governs a lot of what's going on, yeah? So here, also when sort of, I mean, there's people sort of who think really about the ergodic theory of what's going on here. I don't, but other people do. So And so here you see sort of all these kind of flow lines, of course, coming out of here. Yeah. Okay, so so maybe that's enough drawn. And so what you can do now is, so let me just copy this picture, because we'll take 2 copies. We'll sort of do 2 different things. Or what I guess Thurston and Sullivan tell us to do, right? So they say, well, I mean, imagine now you just draw yourself, say, a circle around here, yeah? Draw yourself a circle around here. And now you flow it from time 0 to time 1. Okay, so if I flow it to time 1, I sort of see something like this here happening, where I get this kind of, yeah, I get sort of another circle that I've flown to here. And this gives me an affine structure on the torus. I mean, this gives me a structure on torus. On the torus. Yeah, by really just now gluing it together. So I have this kind of holonomy, it's cyclic. Yeah, it's a cyclic group. It's just generated by A sub 1. Yeah, so A sub 1 generates a cyclic group. And this way I get these kind of structures here on the torus. Yeah. And well, what kind of structure is it? So if I look at the image of the developing map, right, it goes all the way out to infinity. Sorry, it doesn't. So it has, right? I mean, if I flow backwards, there's sort of this barrier here. There's this line here that stops it. Yeah. So I sort of flow the circle sort of back here and also back here, but it's sort of stopped. It's stopped by this line. Yeah. So the image basically now is this developing map is contained in a patch that's kind of P2 minus the line that's sort of spanned by E1 and E2. Okay, so in that sense, right, we get sort of an affine structure. And this affine structure, I mean, it's not a Euclidean structure, because this one here is not a Euclidean isometry, but yeah, it's a perfectly fine affine structure. And now another thing I could do is I could just do something slightly crazier and just draw. I mean, really, you can just draw any old circle you like. Maybe this is a bad color because the contrast is not so good. So let me take pink. So I can draw any sort of curve. The only thing I have to watch out for is that I'm sort of transfer to these flow lines, right? But here sort of drawn something. And you can, again, you take this curve and you flow it to times 1. And this way, again, you get some other structure on the torus, yeah, with the same holonomy. So other structure. With same holonomy. Okay, and to see that it's a different structure is you think about where actually, what's the image of this developing map? Where can I flow? And you see that really, because of the way I sort of set things up, you basically get everything except for these 3 points. Yeah, so the image of the developing map in this case, so the image of this kind of developing map is RP2 minus 3 points. Yeah. And so these are certainly different. Yeah. Here I had RP2 minus a line. Here I have RP2 minus 3 points. So if you sort of generally think about sort of just representations and want to make them into something geometric, that's kind of a challenge. And so that's a challenge I really like, but I don't know how to address it. Yeah, so the challenge is, and I give you the interior of some compact connected N manifold, and I give you all representations into a projective group of the right dimension. And then the question is, so let me formulate it in a slightly positive way. So is every homomorphism the holonomy for some say, meaningful structure on M. Yeah. So I think that's sort of a fun thing to play with, and maybe also that sort of leads to the discovery of interesting geometries, but who knows? Okay. So let me maybe so focus. Here's a cautionary example actually for this question. So there's some really nice examples due to Anderson Canary. So what they do is they take the interior of a compact 3 manifold, M, and then they have holonomies of hyperbolic structures. And so M basically, the boundary of M is some homogeneous surface. And they have these holonomies of hyperbolic structures on the 3 manifold. But then they concoct a limit of these representations where the limit is a holonomy of some hyperbolic structure, but on a manifold that is homotopy equivalent to M, but not homeomorphic to M. Okay? Homotopy equivalent, but not homeomorphic. So already when you were to take up this challenge, right, and the question is then, what does this representation here mean for M? Yeah. So you can't just sort of take the quotient by hyperbolic space by it. You need to do something else. Yeah. And that yeah, seems interesting. Okay. So let me move to a more tractable setting. So we have these notions that we say a domain is properly convex if the closure is contained in some affine patch. And it's strictly convex if it's properly convex and the boundary contains no line segments. So these are key definitions. And then I want to talk about the real projective structure on an N manifold. And I will say it's properly convex or strictly convex if, and so we want three things. So first thing is we actually want the developing map to be an embedding. So we're ruling out sort of the other things that I showed you before with these affine structures on the torus, for instance. Here we want the image of the developing map to be an embedding. The holonomy, a useful thing to ask for is that it's discrete and faithful, because then we can think about taking the image of the developing map and dividing out by the image of the group, and that's really our manifold. Yeah, and so and we call this manifold properly convex if this image of the developing map is properly convex. We call strictly convex if the image is strictly convex. Yeah. So for instance, the Euclidean structure is not something we think about here because the Euclidean structure would not be properly convex. Okay. And so then I look at the set of all sort of representations. So these homomorphisms of the fundamental group into PGL n+1R. And one thing we also like to do sometimes is to take the quotient by conjugation. And so I call this here the character variety. Although strictly speaking, you might be unhappy that I don't take the algebra geometric quotient here. To keep things simple, I just take the quotient. Okay, and so then inside the set of representations, we have those holonomies of properly convex structures, and we have those holonomies of strictly convex projective structures. And so the question is, what is the structure basically of these subsets inside here? What can we say about them? How can we characterize them? Can we compute them? And of course, this cautionary example, the Anderson Canary example, that still applies, right? Because that already fits the bill that we have sort of holonomies of strictly convex projective structures, and they converge to something that's not a strictly convex projective structure. Yeah. So so this is something then that one needs to either deal with or have hypotheses that avoid this example. Okay. So here's some well-behaved settings maybe that I could talk about. So for closed manifolds, basically things are actually very clear. So then if you have any strictly convex projective structure, then every properly convex structure is automatically strictly convex. Yeah, so these sets are the same. And in terms of this inclusion, I mean, we asked, how does it sit inside here? Yeah, how does it sit inside this kind of representation space? And so Kozel, so this is in the 60s, showed it's an open subset. And then that's also a closed subset was shown by Choi and Goldman for surfaces, and then by Kim for 3 manifolds, and then general proof in all dimensions was given by Benoit in 2005. Okay, so this is closed manifold. So closed manifolds behave well. And what I want to give you sort of later in this talk is sort of a maybe sketch proof of how one can sort of streamline some of Benoit's arguments. Okay, and then another thing, for instance, punctured surfaces. So there's work by Fock and Gonchar from 2007 that basically explains how they work. So there, if you look at sort of these properly convex structures on a surface of genus G with n punctures, then it's a bit like Teichmüller space. Yeah, so it's a ball of some dimension that depends on the genus and the number of punctures. And this here is a connected component of some semi-algebraic subset in this representation space. And so what I've written here, VFG, I mean, this here stands for virtual flag groups. So flag is really just an inclusion, if you wish, of vector subspaces. Yeah, so V1 properly contained in V2, properly contained in V3 in this case, which is R3. Yeah, so you just have a line and a plane in R3. And of course, in terms of projective geometry, this is a point contained in a line contained in RP2. Yeah, and they're supposed to be preserved. So the situation is that every peripheral subgroup is supposed to preserve such a flag, at least up to finite index. Yeah, so that's what the sort of virtual means. So so peripheral elements. So the what we sort of run into here is sort of the classification of job normal forms, and they tend to be more interesting than if one just does hyperbolic geometry in projective geometry, right? And so your 3x3 matrix, you might just have 3 blocks, or you could have 2 blocks, or you could have 1 block in the job normal form. I'm just talking about the surface case here, right? And so in this case here, I mean, what are the flags? You really have sort of, here you then have the 3 fixed vectors. And for each vector, you also have sort of 2 lines actually that are fixed going through it, yeah? And then you basically act on these, yeah? So that's sort of one setting. Well, in this setup here, what you have is you just have, yeah? Oh, that was an accident. You have two fixed points, and then you have also 2 lines that are preserved, yeah? And here you just have a unique for a fixed point and a unique line. And they're also kind of related to the volumes, say, of these structures. Yeah, so this here is the finite volume case. And this is kind of the infinite volume cases. Okay. Yeah, so to see virtual flags in action, right? I mean, so if you had something like say you have some kind of surface, maybe I'll draw it with 3 cusps, yeah? And here's your surface. And then maybe, so here you have maybe gamma 1, gamma 2, gamma 3, and maybe, right, you've chosen some triangulation where there's also a triangle. So with vertices at the 3 ideal points here. So, so if you think about sort of the fixed points of gamma 1, gamma 2, gamma 3, they form some kind of triangle. Yeah, so this is sort of, and then each of them preserves a flag. So gamma 1 sort of preserves another line somewhere. And so gamma 1 acts on this and preserves the line, preserves the point. And then gamma 2 preserves a line somewhere. and acts on this and preserves the line and the point. And then you have sort of gamma 3. My lines are not going to be too straight here. So gamma 3 may be preserving this picture here, right? And so now you're acting on this, but you're preserving these lines, and that gives you some restrictions on how you now move, say, this triangle around here, because now you just know that, and sort of think about how you act here, right? I mean, you fix this point, you fix this line, and so this triangle has to go somewhere, right? And you sort of see a picture maybe emerging like this here, and you get also another line here, and you keep going, and you see another line here, and you see what's happening, right? And you really sort of very nicely get sort of a sense of what your domain is like by just iterating these kind of pictures, yeah? And this is also how sort of the pictures on the opening slide were kind of generated, yeah? Just using this. So you can sometimes really think of your domain omega as so some increasing union of simplices or some decreasing sort of intersection of half spaces. Yeah, what we have here, sort of we're intersecting more and more half spaces to see what our domain is like. Okay, and this is kind of what the virtual flags sort of look after. Yeah. Okay, maybe are there any questions at this point? No?
Any question from the audience?
Yeah.
So when you say virtual flags, okay, so why you are calling it virtual? I mean, is in the boundary? I mean,
oh, it's so the thing is that here, I mean, for the surface, they're actual flags, right? For the surface, there's nothing else that happens. So in higher dimensions,
yeah.
So then you look at your peripheral subgroups, yeah? And your peripheral subgroup is of course going to be more complicated, right? It could have
yes, a peripheral subgroup. Peripheral subgroup means something which contains a parabolic element, right, or unipotent element.
Oh yeah, no. In my case, I really think of this as say, so you have your compact manifold M.
Yeah.
And M bar, yeah, I mean, M is really the interior of M bar, yeah, but M bar might have some boundary components, yeah, so so inside here, maybe you have B contained in the boundary of M bar, yeah, and then I call so then you have the inclusion of pi1 of B into pi1 of M, yeah, and this here I call a peripheral subgroup. Yeah, so and yeah, so I mean, you can already think, I mean, say if you look at hyperbolic n manifolds, right, and then you have n-1 dimensional tori, for instance, in the boundary, yeah. And so if you look at the representations of such n-1 dimensional tori, I don't even need the induced representation to preserve a flag. It's enough that it preserves a flag up to passing to a finite index subgroup. And so that's why it's called a virtual flag group rather than a flag group, what we need. Yeah, so virtual just means up to finite index.
Oh, I see. So it's like, you know, that virtual property of a group. That's what you are meaning.
Yeah, exactly. Yeah. Okay. And so in this case, it's enough, right? And when you have this, I mean, if this finite index subgroup preserves a flag, sorry, yeah, if the finite index subgroups preserves a flag, right? Then what the sort of other elements can do that are not in this, they can just permute this basically. Yeah. Mm-hmm. Yeah, so this is, and this seems to be, I mean, technically it does make things more complicated. And it seems to, yeah, give at least here the right result. Yeah. Mm-hmm. Okay, so I should ask, when am I meant to stop?
At 5 o'clock. So if
5
you have
o'clock.
5-10 more minutes.
In 8 minutes. Yeah.
Yeah.
Good. Yeah. So I just want to give sort of an overview of what is involved in now trying to show that this kind of space is open and closed. And the easiest case to really do this is in the closed case, because we don't need to worry about what happens along the boundary, yeah, because sort of boundary gets a little bit messy. And so the classical result, so Kozo tells us the space is open, sort of properly convex. And then Benoit says that if you have strictly convex structures, of course, these are the same, and this here is closed. Yeah, so then this is open and closed. And so what I want to give you is kind of the ingredients. I mean, what makes this work? And if you want to look at it, there's a paper by Darrell Cooper on the archive that focuses just on this, in this case here, to make things seem easy. So we need to think about such limits. So we have our manifold and we have our domains divided by some groups. Yeah. And so we assume we have some kind of sequence of representations that converges. And we want to show that the limiting representation is also coming from a strictly convex projective structure. And so, well, you might wonder, why is this difficult, right? We already have the representation. But the problem is that when you look at these domains, as they sort of change, they might actually collapse in the limit. Yeah, so that's really the issue. Yeah, that all of a sudden you have these n-dimensional domains, but then as you take sort of a limit of these domains, they collapse. So there's a nice fact due to Pensacree. Pensacree tells you that actually, what can you do? So if you have any old domain, I don't care which one, and you pick any point in it, I don't care which one, then you can find a projective transformation that puts your domain very nicely between the ball of radius 1 and the ball of a radius that only depends on the dimension, but not on your domain and not on the point. And your domain sits between these two balls. So this is kind of a compactness result, because it means, yeah, if someone gives you now this sequence here, right? We can now, instead of taking this sequence here, we can just apply these matrices T, one for each of them, right? And now, so here, sort of my T case, I have my P case. And now I can wonderfully just put them all into the same setting and then subconverge these domains, yeah? So what's the problem? Well, the problem is that in doing this conjugation here, I don't have any control over the entries in my limiting representation. So all of a sudden this might blow up, yeah? So I might actually not have a representation anymore. Yeah, that's the entries in these matrices might just go to infinity. So that's the problem with trying to do this. And so in the sequence, right, when we do the sequence, we sort of do some kind of normalization. Whatever normalization we do, we need to control both the domains and we need to control the representations. And so Benoit's strategy was, well, he says, first, I sort of aim to show that the limiting representation is irreducible, and then use this fact to rule out collapsing of the domains. And this involves some really complicated arguments. And so our strategy was to, because his approach did not work in the case of non-compact manifolds. So we need to think of something else. And so our strategy was to first actually prove that the domains, you can sort of make your domains converge to a properly convex domain of dimension n, on which your representation rho infinity acts, and then also to show that this representation that you have is discrete and faithful. Yeah? And then these two things, it's not so hard to see that they actually imply the closed result. So how do they imply the closed result? So now we get this kind of other manifold, right? A bit like in the Anderson-Canary examples, right? We get some mystery manifold that's this quotient here. But now because M is closed and have isomorphic fundamental groups, yeah, because they're both these kind of quotients, there's an algebraic topology argument, because this is a K pi 1, to argue that N is also closed. So that's the first thing. Then there's this fact that I told you that actually strictly convex, so M strictly convex then implies N is strictly convex. So here we only knew this domain is properly convex, but now we know something about the fundamental group, and so it's strictly convex. And then we sort of work in the parameter space for n and say, well, this one we know is open. That's what Cursor tells us. And we also know that these representations are near these, and these are the same groups. And that actually implies that M is homeomorphic to n, yeah, because they're both homeomorphic to quotients of this representation here. And so this gives you the result. So this is how these two properties help you. And so how do you show these properties? So let me just sort of give a very quick argument. I mean, I said we need to make sure that we can't just sort of apply any old Benzo-Curry domain map. We need more control. So the first thing is basically imagine, right? I mean, imagine you have a globe. Imagine you sort of look at any old set on your globe. Yeah, maybe the map of India. Yeah? India is maybe not convex, but doesn't matter actually. You can apply this to any set. So here you have India. What you want to do is you want to now basically rotate this whole thing such that basically when you now sort of project, right, project the map of India onto a wall, yeah, then basically the origin, this is where the centroid of India ends up. Actually, I have no idea. I should have looked this up. Do you know what the centroid of India is? I also don't know it for Australia. I mean, somewhere there will be, yeah. So the centroid ends up here.
Yeah. Go ahead. Yeah.
Yeah, so the centroid ends up here. So now all these domains sit in the same patch, and we have some control because the centroids sit all in the same place. And then we sort of apply Fritz John's result that says, well, actually, there's a very special, unique ellipsoid of maximal volume in a convex body, such that this ellipsoid is contained in your domain. And if you scale the ellipsoid by the dimension n, you're also contained in here. So you have this nice unique ellipsoid. And so now we rotate a bit more so that the principal axes are actually the coordinate axes. Yeah. And so again, I mean, so both of these things, I've just done rotation. So that's just a compact change. And so I don't have any blow-ups, right? But now I want to scale with diagonal matrices so that basically I get sort of after the scaling, I get the scaled thing sitting between just a unit box and a box of some controlled sort of size. Okay. So here then, this is again the same issue you will tell me, right? And this is again the issue here when I do this. How do I know that entries of my matrix are not blowing up, are not going to infinity? And there's a thing that, I mean, Daryl discovered this using non-standard analysis. But then, of course, in our paper, there's just an analysis proof that you could do in high school. It's a really nice sort of argument called the box estimate that basically controls. So if you have any old matrix and it takes a box to a constant times the box, then you can control the size of all the matrix entries by this constant that you have and the size of the bottom right entry. Okay, so that's it's actually maybe a nice thing to do is give this as an exercise, yeah, or as an exercise to your analysis student. So this estimate is now not changed by conjugation by a diagonal matrix because we're looking at the bottom right entry, and so this basically then tells you that when you do this kind of change, because here here I'm in a situation that these things here preserve the box, and these are diagonal matrices that are scaled by, and now basically then you see that whatever you get here, the bottom right entry is really sort of bounded uniformly by the bottom right entry of this one here, just because of this box estimate. So that's roughly it, and then one other thing that you need to sort of contend with is that you first maybe get the wrong kind of representation, and you sort of apply another sort of wonderful result called Chakros theorem that basically tells you that when you sort of take limits of discrete and faithful representations, the limit will be discrete and faithful again. So this way, this is where for us then irreducibility comes in quite late in the game, not as early as for Benoit, to basically conclude that whatever representation we get is conjugate to what we had. So anyway, so that's kind of the the short story of how we get this, and then basically just put the pieces together in the way I just told you. Anyway, so sorry for non-compact manifolds is all on the archive. So maybe you would like to have a look. And then here's a little bit of advertising. So with 2 students, we've written a book just sort of looking at the case of surfaces that sort of goes through these kind of elements of projective geometry in sort of the easiest setting. So anyway, thank you very much. Yeah.
Okay. So thank you, Stephan, for this wonderful exposition of recent work on convex projective structures. So is there any question from the audience? Anyone? Any questions?
Is there any results for in general surface boundary compact boundary?
Your voice is breaking. So either you can repeat it or maybe you can type it on the chat box and I can read it out. Yeah, your voice was breaking, so I could not understand. I think Stephan also couldn't understand.
Yeah, sorry, I couldn't understand. But yeah, if you put it in the chat, I can read it.
So can you write it in the chat box? So probably he is asking whether there is any result about, I think, maybe of manifolds with boundary or surface with boundary, that some sort of that thing.
Yeah. So surfaces with boundary, I guess we had sort of these. Let me just go there. Here. And this is basically what happens here in these kind of pictures here. So this is one way to think about what's happening here is, say you have if you even think about sort of a hyperbolic surface with totally geodesic boundary. Yes? So really it would sort of flare out. It would sort of have a flare here. Here's sort of a geodesic, right? The unique geodesic in this kind of neck here. And then it sort of goes out. So what does it look like, right? I mean, you have the hyperbolic plane here, and then you have sort of the boundary curve. If you look at the orbit of this gives you all of these kind of segments here, right? And if you look at, so if this is gamma, then gamma basically has an attracting and repelling fixed point. So here's gamma plus, here's gamma minus, yeah? And this is what you can think of as, say, these points here, yeah? And then actually there's lots of options. I mean, you see here for this domain, right? I mean, you could take as your domain just sort of this very small domain here, yeah? Or you could take, I mean, you could sort of, there's a third fixed point that's actually determined by, you take these lines that are preserved here, these tangent lines to the circle. So everywhere here, you can sort of, you see these tangent lines to the circle at these kind of fixed points. And so you could make the domain bigger, and you could say, actually, I put on also these kind of triangles here, yeah, and call that my domain omega. That would be another structure. It has the same holonomy, but it has a different developing domain, because here's sort of the smallest domain you could take. Here's the biggest domain you could take. But of course, you could also take lots of things in between, yeah? Especially with, I mean, you could sort of make smooth boundary, you could have piecewise linear boundary. And yeah, there are lots of options here. Yeah.
Yeah. So is there any more questions?
Yeah, I have one question. Hello, sir. Could you please go back to the page where you explain the action of those maps with 3 points and the one, the todas, how to get the todas?
This one here. Yeah.
Yeah, the right side, pink one, pink picture. You said we'll get a todas from that one also, right? If you traverse for time t1.
Yeah, exactly. So I travel to time t1. So if I look at where it goes, right? I mean, here sort of I pushed in this direction, and here sort of keep pushing in this direction, and then here you see how, yeah, right. And
but the intersecting points won't they cause any problem for being smooth manifold?
Oh, no, I mean, you can really just sort of think of it if you wish, right? I mean, think of it as you have sort of the strip that because you really only need to know locally, right? And we're building an atlas for our surface. I mean, here's my torus, right?
Right.
And so maybe if I think about this patch here, right? This part here, say, yeah.
Right.
This might be sort of a patch here in my atlas, yeah. And then if I think about sort of what's here, yeah, that might be a patch over here for my atlas, right? And I'm really just building atlas for this structure.
Right.
Does that make sense? And of course, if I draw it all the way, right? I mean, here, sorry, and here, of course, these two identified. So really, this goes all the way around, yeah. So yellow goes all the way around here, and the green goes all around here, yeah.
Right. Okay.
Mm-hmm.
So also in you draw a picture of a threshold torus with 3 genus torus, right? Towards the end. Yeah. Could you please go back to the gamma 1, gamma 2, gamma 3?
Yeah.
Right, this one. So sometimes it might happen that when we're doing some ideal triangulation, two angles of one triangle might spiral along one cusp of the surface, right?
Mm-hmm.
For example, one punctured torus.
Exactly. So all of them. Yeah.
Right.
Mm-hmm.
So in that case, this is not gamma 1, gamma 2, gamma 3 in the left hand side, the triangle you have drawn.
No, it's conjugate. I mean, I could have equally sort of said here, I mean, this is gamma 1, and then really gamma 2 might be some alpha, gamma 1 alpha inverse, right?
I see.
Yeah, it could have been, yeah, I just want to keep it simple. But yeah, I mean, they're just basically, because all these peripheral, right, I have this peripheral subgroup here, but then, I mean, there's, this embedding gives me one choice, but then I need to consider all the conjugates as well. Yeah. Mm-hmm.
Right. Okay.
Yeah. So all of these points here that I get then by iteration, right? They're going to be conjugates of these ones. Yeah. Mm-hmm.
Right. Okay. Thanks. Right.
Yeah.
Yes.
But no, it was a very good observation. Yeah. I just try to not put in this detail.
Okay. Thanks.
Okay. So any more questions? All right. So if there are no more questions, then it's already very late for Stephan. So thank you, Stephan. Thank you very much for spending some time with us and giving this colloquium. So I hope to see you in person sometime at IISER-Mohali. Yeah. So
yeah, thank you very much. Thank you very much for the opportunity to give a talk, and thanks for all your great questions. Yeah.
So thank you very much. So let's give a big hands to Stephan virtually. Thank you very much.